Okay, so today we're going to be doing section 6.4. So as you can see here, in previous lessons we learned how to graph quadratic functions and identify its key features like the vertex, axis of symmetry, y-intercepts, some x-intercepts. We also learned how to write quadratic functions from given information. So like if I knew the vertex, I can put it in a vertex form, things like that. Okay, today we're going to continue this process of writing functions, but we're going to do it through the real life problems. So we're going to be looking at some real life problems here. And so to start us off here, we're going to look at first one, which is called vertical motion. Okay, vertical motion problems. These are projectiles. So if you ever throw something or shoot something out of a cannon or anything that gets launched in any fashion, okay, this is the model that is used to compare the height of the object versus time. So the height of the object is over a time. That's what this model is right here. So this also includes things that are dropped. So if you're at the top of a building and you just drop something, this is also the model that you can use and in certain values and stuff. So let's take a look at this. H of t is the height of the object at a certain particular time. Negative 16 t squared. This negative 16 has to do with gravity. And when you take physics and stuff like that, you can get more into detail on that. V sub 0 is called an initial velocity. So if I throw something with a certain initial speed, then that would be what goes here. We times that to t. And then h sub 0 is the initial height. So this is the height that the object is being launched at. T is in time in seconds. So here's some notes over here. So this is what it says. If I'm throwing an object upward with a velocity, then this will be positive. If I throw something down, if I say I'm throwing an object down at 10 miles per hour, then this right here you plug in negative 10. So when it's going downward, we're going to plug in a negative value for v sub 0. And if I'm just dropping an object, just holding it and dropping it with no initial velocity at all, then that means that's going to be 0, and that middle term then is gone. And so that's how what a dropped object does. This term right here is not here. So here's an example that you might see that can use that formula. Write a vertical motion model for an object that is thrown with an initial velocity of 32 feet per second from an initial height of 20 feet. Here's the question. How long will it take the object to reach its maximum height? Okay, so let's talk about this. How do I go about this? Anytime you do a real life problem, you need to read it, make sure you understand things. If they talk about a formula word or a phrase that represents some kind of formula or equation you already know, as in this case, vertical motion model, that is the model. You want to write that on your paper. And then you're going to find the values to plug into it. So you got to find h sub 0, v sub 0, and you write that in there. So the initial velocity is 32. So we would plug in 32 for that. The initial height is 20 feet. So we would plug in 20 feet for that. And when we do, we get this model right there. This is the equation you're going to use to answer this question. What is how long will it take an object to reach its maximum height? So for this one, you need to understand how in all of our problems, you want to make sure you understand what do things mean. What does it mean to reach its maximum height? What is a maximum height in a projectile launch? Well, these are quadratics. So the maximum or minimum is always going to be at the vertex. So what this question is really asking you to do is find the vertex. So let's talk about that. Two questions can be asked about the maximum height. Okay. In this one, I'm asking how long will it take the object to reach its maximum height? And the other question would be, what is the maximum height? When does the maximum occur? This would represent the x-coordinate of the vertex. What is the maximum value? That would represent the y-coordinate of the vertex. Okay? Both answers are found with the vertex. So when does it occur, as in this case, how long will it take, at what time will it occur, and what is the maximum value, which was not asked in this one, just asked when will it occur. So be aware that those two questions can be asked and what the value that answers them is. So in solving this, we got to find the vertex. So this is in standard form, okay, standard quadratic form. So then we want to find negative b over 2a. B is 32, a is negative 16, so a negative 32 over 2 times negative 16, and that gives me a positive 1. I only need the x coordinate of the vertex, so that is the answer. The maximum height will occur at t equals 1 second, and that's how you would write your answer. That was all I was asked in this question right here, so that would be the answer right there, and this is the work that you would show once you had the model. But if the question did ask, what is the maximum height, then I can take this number, plug it in to find the y value. And this is how you would plug it in, what it should look like on your paper. And you see that you get a 36. And so the maximum height is 36 feet. And it occurs after 1 second. That's how these problems are done. So always ask the questions that you're trying to find. Your answer usually is found in that. Here's another example that you can use quadratic for. A rectangular patio has a length 4 times its width. It also has a 3-foot wide brick border around it. Write a quadratic function to determine the area of the patio and border. So we have to write a quadratic function, okay, that will represent this model. To do something like this, we read it and we see, okay, this one is talking about a rectangular shape. When you're given geometric shapes, always draw the shapes. So draw a picture of this. Okay, you draw a picture of the rectangles, you label things according to what you see in here, and when you do, now you'll see most of the work in here, but here is the patio. It's a rectangular shape. It said the length is 4 times its width, so I used x to represent the width, and then the length is 4 times that. So that was a key value thing right there. What does that mean? Okay, what does that mean right there? It has a border around it, and that border is 3 feet wide. So all the way around is 3 feet in all directions. And then it asks for the area of the patio. Well, the patio is a rectangle. So we want to find the area of a rectangle. Okay? And so then we go back over here. We want to find the area of the patio and the border, so all of it. So what is this length? The area formula, you write down your area formula. We're going to find the length and the width of this thing right here, this shape, which is the patio and the border. This has a starting value of 4x, and then I added a 3 on that side and a 3 on that side, and that's why the length is 4x plus 6. For the width, the same idea. The initial start on the patio was x, and then I added a 3 on each side, which gives me x plus 6. Plugging these values into this formula for area gives me the quadratic function model. This right here is the model that represents the area of the patio and the border. And then from this, I can answer other questions, whatever they may ask from it. But you need to be able to get to here. So for problems that describe a geometric shape, draw the shape. If they use a formula word like perimeter, circumference, area, surface area, volume, write the formula down for that shape. Find a variable expression for each dimension, substitute into the formula. So what do I know by dimensions? Well, if there's 2 variables or unknowns in the formula, then there's 2 dimensions, length and width. And so you want to find an x expression, a variable expression for each of those 2 things, and then plug it in. That's what we did here. Let's look at another question. So in this particular problem right here, so Mia tosses a ball or a dog. This is the function that represents the ball's path. Find the ball's initial and maximum heights in feet. Okay, so what does this mean? How do we do this? Well, let's interpret what everything stands for. The maximum height is determined by the vertex. Okay, remember that's from before, maximum height. The x-coordinate is where it occurs, the y-coordinate is what the max is. So you want to find the vertex. It is in vertex form, so it's fairly easy to do. What number makes that 0 is 1, so the x-coordinate is at 1. This right here is k, which is the y-coordinate of the vertex, so k is that. So this tells me that I have a maximum height of 6.25 feet, and it occurs 1 foot from Mia. So you notice there's an x in here. This is not a time. This is a height versus distance. Okay. So 1 foot from Mia, which you threw the ball 1 foot from. When I got 1 foot from her, you reached the maximum of 6.25 feet. The initial height occurs when x is 0, or when time is equals 0. Okay. If you look back at this model over here, if t is 0, then these two terms right here are 0, and I end up with h sub 0 only, which is the initial height. So to find the initial height, you need to plug in 0. So if I give you a model, when you plug it in, it should look like this. You plug in f of 0 equals, you substitute the x as 0 for x, you work this out, and you get 6 feet. So the initial height is 6 feet, and this is the maximum height up here. Okay, so notice in all these cases, in the problems themselves, I'm asking, what does it mean? What does this mean? What does it mean to be the initial height? What does it mean to be the maximum height? Therein lies the process that you follow to solve it. All right, one more example. This is on page 342 of our textbook, but I'll show it to you. So those who may not have this textbook available can see it. So here is the problem right here. A student drops a rock over the edge of a well and hears it splash into the water after 3 seconds. Write a function in the form, this is our vertical motion problem, to determine the height of the rock above the bottom of the well t seconds after she drops the rock. What is the distance from the surface of the water to the bottom of the well? Okay, so we need to write a model here. This model requires me to have an initial velocity and an initial height. Okay, but what we're interested in is how far it goes. So we want that distance right there. And so the picture shows that the well is above ground level. But the whole well is 200 feet long. So when you see a picture associated with this, look at the picture. Okay, so since the whole well is 200 feet, whether the top of the well is above the ground a little bit or at ground level to begin with, doesn't matter because the whole well is only 200 feet deep. And I want to know how deep the water is at the bottom. So I say that because I'm going to use the initial height of 0 because I don't know how high the thing is above the ground. But also I wanted to make sure you understood that it doesn't really matter. Okay, so there's our picture. Let's go ahead and I'll come back to it in a minute. I'll show it again, but usually what I do is I redraw the pictures. Okay, but I want to talk about how to start this problem. So how do I start? When somebody sees this question like this, they usually don't know how to start this thing. Let me zoom in a bit so you can see some of my small writing, unfortunately. So how do I start? Write the formula down. Redraw any pictures that's associated with the problem. So we had a picture in the book, but I'm going to redraw it. I'm going to identify the stuff in the picture that I know. It's 3 seconds to hit the water. A dropped object has initial velocity of 0. So remember it said we are dropping a rock. So that means the initial velocity will be 0. And like I said before, we're going to drop at ground level, so h of 0 will be 0. And that's because the well, like I said, is a standard 200 feet. And so I can just kind of act like it would squish all the way in the ground. Some other questions you ask yourself. What do I want to know? If you don't know what you want to know, then you don't know where you're going. I need to know how deep the water is. What do I need to know to find it? These are the questions you always ask yourself. What do I need to know to find it? Well, you keep asking this question as you identify this. What I need to know. You keep asking these questions until you get to a point where you can find how to do something. Okay, so you can actually find the answer. So sometimes it might be a string of what do I need to know is what do I need to know. If I need to know this, then how do I get that? Well, how do I get that? And then you keep backtracking until you get it. If you can find anything, at least you have, so I think I should say if you can't. If you can't find anything to find, let's put a can't in there. And what you've done is at least you have a string of questions that you can ask the teacher when you come into class. Okay? Showing that you've attempted the problem, but you're not sure about some things, and that's where you learn from. So here's the question. Let's go ahead and take a look at it. Show you what I did. I redrew the picture. Here's my water. Okay, it's 200 feet. I'm going to drop a rock. It's going to hit the water after 3 seconds. Okay, I said the initial height is going to be 0 because this is at ground level right here. Velocity is 0. So that means these two terms basically go away, and I'm left with just this part. I know it hits the water after 3 seconds. I'm trying to find this depth. So what do I need to know to find this depth? If I can find how deep it is from here to here, then I can subtract it from 200 and I'll have that depth. So that is my game plan. Always have a plan of what you're trying to accomplish. Don't just do things, but know why you're doing it. So if I can find this height, I know it takes 3 seconds. So that means time is 3. So I'm plugging in the time into this formula of 3 seconds. At negative 16 times 3 squared, that's 9. 9 times 16. So we get a negative 144. So the rock falls 144 feet before hitting the water. So I know this distance right here is 144. So that means the depth of the water then is 200 minus 144, or it's 56 feet. So the whole point of doing word problems is to understand what it is and what it is you're actually trying to find, and then devise a plan to get to that. You do all that before you even attempt to solve the problem. You don't start plugging numbers in until you know what's going to occur. If you just start doing stuff, you're always going to get lost and always confused. Okay? So we'll do some more problems together in class. I'll see you then.